Last time in class, we learned that a system converts input signals into output signals. We looked at the four most common types of input signals, which were the impulse, the step, the ramp, and finally the sinusoid. Today, we're going to be focusing on the output signals. An output signal also has another term. Sometimes it's called a response. The system response will be different depending upon the input, and we can look at these different kinds of responses by matching the response to the input. In other words, we can look at a system's impulse response, its step response, its ramp response, or its response to a sinusoid, which has a different term. It's called the forced response. Since the sinusoidal response has its own term, being called a forced response, the other three responses also have a special term. The response to each or any one of the first three is known as the natural response. As we go through and look at what each of these different kinds of responses look like, you'll catch on to why the first three are grouped together and are called natural responses, while the sinusoidal response is in its own category termed the forced response. Now, different systems respond different ways to the different input signals that we can give to it, but as it turns out, all systems primarily fall into one of two different categories. The first category is called first-order systems, and the second category is called second-order systems. Even though each individual system has its own behavior in response to different kinds of inputs, we can simplify the process of learning about the different kinds of behavior by focusing on first-order and second-order systems. Since almost all systems are in one of these two categories, if we just learn about the properties of these two categories, we will have a great deal of insight into most of the systems that we will encounter in our lives and careers. Let's take a look at a couple of examples, both for first-order systems and for second-order systems. Let's start out with the first-order systems. One example of a first-order system is a thermometer. Here, the input signal is the temperature in the outside of the thermometer. The output is the temperature of the inside, or another way of saying that is the height of the fluid on the inside of the thermometer. When the input changes, that is, when the temperature on the outside of the thermometer changes, the output, the temperature on the inside of the thermometer, will begin to change as well, and as a result, the height of the fluid will increase. The thermometer is a type of first-order system that converts the input, the temperature on the outside of the thermometer, to the output, the temperature on the inside of the thermometer. Another example of a first-order system is an RC circuit like the one I'm showing here. Here the input is the voltage over here on the left, and the output is the voltage on the right. When the voltage on the left changes, the voltage on the right changes also. The relationship between the input and the output signals is a first-order relationship. That means that the relationship between the output and the input signals in this RC circuit will have the same kind of a characteristic as the relationship between the output temperature and the input temperature in the thermometer. This might be very surprising to you, since the circuit and the thermometer are very different kinds of systems, One deals with heat and the other with electricity. But, as we'll learn later on in the class, these two very different systems have very similar mathematical underpinnings, and so the two systems end up behaving very similarly to each other. That's part of the magic of systems modeling. Systems that are very different on the surface can actually be very similar underneath, and by learning only a few characteristics of standard systems, we can understand a large portion of the different kinds of systems around us. Here's one more example of a first order system: a mass sliding along a floor with friction. Here, the input is the force with which the person is pushing the object. There's another force on the object that is friction from the floor, and then the output signal is the velocity of the object sliding along the floor. This system is again very different from the thermometer, and it's very different from the RC circuit, but as it turns out, it behaves the same way. Now, let's take a look at the similarities of how all of these first order systems behave. The most interesting of the similarities between how a first order system behaves is found in the first order step response. I'm going to draw you a picture of what the first order step response looks like. The x-axis will be time, and the y-axis will be the output. The first order step response looks like this. Do you remember what the step input looks like? The first order step response is the response or output that the system produces when you give the system a step input. The step input looks like this. This means that all of our first order systems, if we give them a step input, will have a response that looks like this plot. For example, if we're looking at the mass sliding on the floor, this means that if we suddenly apply a constant force to the object, the chair sitting on the floor, the velocity will start by increasing very fast, and over time it will slow down its rate of increase until it stops or comes to a rest at a constant velocity. This response also applies to the RC circuit. If we suddenly, for example, close a switch on the left side of the RC circuit, the voltage input will jump and produce a step input. Then, if we would watch the voltage in the other side of the RC circuit, the voltage would start by increasing very quickly, and then it would slow down its rate of increase until it came to a steady, constant voltage. The thermometer also would behave like this. If we would suddenly drop the thermometer into a cup of water at a constant temperature, that would be giving the thermometer a step input. We would be suddenly changing the input temperature, the temperature on the outside of the thermometer, to a constant value. The temperature on the inside, or the height of the fluid that we would watch, would quickly increase, but then over time it would slow down its rate of increase. Now, right away, you'll probably notice that this step response does not look like the way that your Slinky behaved when you gave it a step input. For one thing, there are no oscillations here. In other words, this is not a sinusoidal output. That should give you a clue that your Slinky is probably not a first-order system. When you are trying to model a system, one of the first distinctions that you should make is whether the system is a first-order system or a second-order system. Now, besides the fact that the step responses all look similar, there's a second surprising similarity in the responses between all of these first-order systems. In order to help you see what this interesting similarity is, I'm going to redraw this output a little bit differently. I'm going to give it a more pronounced or obvious, easy to see slope at the beginning. Now, let's suppose that we would take this response and we'll find its slope right at 0, and I'm going to draw a dashed line so that the slope of the dashed line matches the slope at the very beginning of the step response. I'm also going to erase the input, and instead I'm going to take another line. I'm going to find the value where this output will stop changing at its what we call its steady state value, and I'm going to draw a dashed line back. So this purple dashed line, that's the steady state value. In other words, it's the value where the step response stops changing, or the value to which the step response converges. Next, I'm going to take this intersection point between the steady state value and the line that matches the slope of the response. When I draw this line down to the time axis, this amount of time from the beginning to this intersection has a special term. It's called the time constant. Now, if I take the intersection of this line and I dash it back out to the output, I will find that this point of the output is 63.2% of the way between 0, or the starting point of the output, and the steady state value of the output. The surprising thing here is that this relationship is always true. It's true for the mass sliding on the floor, it's true for the RC circuit, and it's true for the thermometer placed in the water. Now, I know that the number 63.2 might seem like an arbitrary number, but hold on for just a moment and perhaps you'll start to see the pattern. Now, what I'm going to do is I'm going to take the slope of the line at this new point, and I'm going to dash a line that is tangent to that point once again. I'm going to find the point where this new line intersects the steady state, and I'm going to dash that line down again. As it turns out, this amount of time is 2t. In other words, the amount of time in here is also another time constant. If I would then take the intersection point right here and dash it back to the output value, the percentage here would be 86.5% of the way from the 0 output to the final steady state output. I could continue this pattern. I could find the value of this intersection, take the slope, dash that line up to the intersection, take the intersection between the line and the steady state, bring that down, and this would be 3 time constants. If I went and found the value of the output at 3 time constants, that value would now be 95% of the way from 0 to the final value. Do these numbers look like a pattern to you now, or do they still look like they're arbitrary numbers? As it turns out, there is a pattern here, and it's based on the mathematical value e. The mathematical number e is a value that we see popping up in nature all the time, kind of like the number pi is a value that we see popping up in nature frequently. E is approximately equal to 2.718. Now, if I would calculate 1 minus e to the minus 1, it would give us the value 63.2. If I would then calculate 1 minus e to the minus 2, it will give the value 86.5. If we take the value 1 minus e to the minus third, we get 95. These are all percentages. So the first order step response has its basis in some pretty simple mathematical functions. And the surprising and very useful aspect of this is that all first order systems behave the same way, whether they're mechanical systems, electrical systems, or thermal systems. All first order systems have this same property about their time constant and the relationship to the value of the output. As it turns out, the time constant is all you need to know about a system in order to predict its response to a step input. You could find the time constant of a system by doing an experiment, kind of like the experiments that we did with our slinkies in class. Or you can find the time constant mathematically by finding the equations of the system. We're going to be learning more about how to do that later in class, but I'll just give you an example now. In the RC circuit, we can calculate that the time constant of the circuit is equal to the resistance times the capacitance. By knowing this, we could figure out what the step response is for any system with different values of resistance, different values of capacitance. If we need the system to respond at a certain speed, we could calculate what value of resistance and what value of capacitance we would need for the system to respond to a step input at the speed that we want. Here's a nicer picture showing the relationship between the time constant of a first order step response and the value of the output at that time. It also shows you how the time constant is related to the slope of the output. Now, before we finish up with first order systems, I want to take a brief look at the first order ramp response. The first order ramp response tells us how a first order system produces an output in response to a ramp input. So the x-axis will be time, and the y-axis will be the output. Let's suppose that the ramp input looks like this. A first order response to this input will look something like this. Now the input here has a constant slope, as we learned earlier. We used A as the value of the slope, and we said that the equation of this line was then A times t, where t is time. The ramp response in its steady state, that is, the way it is after it stops any of its changing, will also have a slope of A over time. But that's not all we can say about the first order ramp response. We can also say that the distance between these two lines, between the input and the output, is a value equal to the time constant. This is the same time constant that we saw in the step response. If we know the time constant, either by doing a test with the step response or by calculating it by using a mathematical representation of the system, we can predict what the response will be to a ramp input. We can not only know the distance between these lines in the x direction, we also know the distance between these lines in the y direction. That distance is equal to a times the time constant. Another way of saying this is to say that the output is delayed from the input by a time equal to the system time constant. In other words, we can know that if the input has a value of x at time t, we know that the output will reach that same value at a time, capital T, time constant, seconds later than the input. So, by knowing no other parameters of the system other than the time constant, we can predict the behavior of the system to a step input or to a ramp input. And once again, this is true of all first-order systems, regardless of whether they are mechanical, electrical, thermal, or any other kind of system.